So yesterday we learned about the weighted least squares, right? So what we said in the weighted least squares model was, we said and we said right? So we said potentially each of the error terms have a different variance, right? Potentially each of the error terms have a different variance. Sigma 1 square is not the same as sigma 2 square and so on, which is different from the OLS model. In the OLS model, we specifically restrict all the error terms to have the same variance, whereas here we are going to allow each of the error terms to have a different variance. Okay. Now, if that happens, we learn that variance of beta hat is no longer sigma square upon summation xi minus x bar square. That's clear to everybody. So we said we will follow the GLS strategy. What is GLS strategy? The GLS strategy is that whenever the error terms in the regression model do not follow the classical assumption of being uncorrelated and homoscedastic, these are called the classical assumptions, right? Then you transform the data in such a way that the regression in the transformed data has error terms which follow the classical assumption. So basically GLS is modifying. So whenever the OLS models do not have, when your regression model does not the error terms in your regression model do not satisfy the assumptions of the ordinary least square model, the strategy that we use, the generalized least square strategy, is to modify x and y in such a way that the resultant error terms are homoscedastic and non-autocorrelated. Like in the case of first order autocorrelation, we modified the data. We said y star is yt minus phi hat yt minus 1. We said x star is xt minus phi hat xt minus 1, and we got a new regression model where the error term was not autocorrelated. Similarly here, we must think of a way of transforming them. First, let's assume that we know each of the sigma squares. We know sigma 1 square, we know sigma 2 square, we know sigma 3 square. Suppose we know the value of each. Then think of dividing. So the FGLS strategy could be, think of dividing each value by sigma, each of yi by the appropriate sigma I. This will then be So let me call this y star I. Let me call this y star I. Right. Let me call this y star I. Alpha star. Where this whole thing I will call Vi. Right, so Vi essentially is EI upon sigma. So the point that I said yesterday was variance of Vi is equal to variance of EI upon sigma I. Sure? Which is equal to because variance of EI is sigma square I and variance of x upon alpha is 1 upon alpha square variance of x. Sure? So this way, if we can transform the y, so what have we done? We have transformed y and x in such a way that the error terms in the resultant equation are no longer heteroscedastic. They have a constant variance. So we have done a GLS. Right? So we have done a GLS. But this is possible only under a strong, there's a strong requirement for being able to do this. And what is that requirement? We should know all the sigma square i's. We know the variance of each of the error terms. But that is not going to be true because we don't observe the error terms. Each of the error term comes from a probability distribution. We don't know what that probability is. We know it's normal, we know it's mean zero, we know it's got some variance, but we don't know what is that value of that variance. So in practice, this seems to be a difficult thing. So it's a strategy, but it's still not a feasible strategy. So we need to make it a feasible strategy. Just like the case of autocorrelation, where we had a GLS estimator, we said yt minus phi yt minus 1 is alpha into 1 minus phi plus beta xt minus phi xt minus 1 plus et minus phi et minus 1. So we say you first lag the value of yt by 1 period, then multiply throughout by phi, then create yt minus phi yt minus 1, etc. so on. But you could not do that without knowing phi. So the idea is to estimate phi. The idea was there to estimate, to make a feasible device. So to make this feasible, what will we have to estimate? Sigma I square. We'll have to estimate sigma I square. Right. Now what is sigma 1 square, for example? What is sigma 1 square? The variance of the first error, E1. Sigma 2 square is the variance of the second error, and so on. Now, suppose you want to estimate the variance of a population from a sample. What would you do? Suppose you have a sample of size n, x1, x2, x3, x4, xn, and you want to estimate the population variance sigma square from this. What is the estimator for the sample? The sample variance. So what will be the formula for the sample variance if you have n observations? Summation xi minus x bar square upon n minus 1. Right. Now here we are a little bit lucky because we know what is mu. We know the population mean is 0. For each of the EI, expectation E1 is equal to expectation E2, all of them are 0. So we don't really need to bother about x bar. Right, so it will be summation xi minus 0 whole square upon n, not n minus 1, because now x bar is not estimated. Right? So it had to be summation xi square upon n, that is summation of the various values of E1 square. So suppose you observed n values of E1, then you will find the variance as summation ei square upon n. Right? Summation ei square upon n. Right? But do you observe n values of E1? No, you just have one value of E1, no? E1 hat. Right? So the argument could be that we use E1 hat square as an estimator for variance sigma 1 square. E2 hat square as an estimator for sigma 2 square. E3 hat square as an estimator for sigma 3 square. And that's nothing, in a sense it seems to be a good idea. Because expectation E1 hat square will be equal to sigma 1 square. Because if I ask you the question, expectation E1 hat square. Right, what is expectation E1 hat square? The average value of E1 squares. Any of the n values can be E1. So the average value of E1 hat square will be nothing but sigma 1 square. So if I use E1 hat square as an estimate for sigma square, I will get an unbiased estimate. Right? So I use E1 hat square for sigma 1 square, E2 hat square for sigma 2 square, E3 hat square for sigma 3 square. So one possible way of thinking about this could be to say, instead of using 1 upon sigma 1 square, 1 upon sigma I write 1 upon square root of E1 hat square. Instead of writing 1 upon sigma 2, I write 1 upon square root of E2 hat and so on. But that's not such a lucrative strategy. What do you think could be a problem with this kind of a strategy? What could be the problem with this kind of a strategy? Think of consistency of estimates. So the problem is, suppose I want to estimate population mean mean. I have a sample of size 4. I form x1 plus x2 plus x3 plus x4 upon 4. I've got 4 independent bits of observation to estimate that one parameter. Now suppose the sample size increases from 4 to 20. So I have 20 independent bits of information to estimate that one parameter mean. Right? So as the sample size goes up, my information actually increases because the number of parameters I want to estimate remains only 1. But the number of data points that I have keeps on increasing. So, right, and which would mean that my information gets better and better and better. If my information gets better and better and better, the variance of the estimator will keep on becoming smaller, which is nothing but consistency. So to make an estimate consistent, it is important that the number of observations increase while the number of parameters estimated remains the same, or at least does not increase as fast as the number of observations. Is this clear? Yeah, so for example, if you are a policeman and if you are keeping tab on, so you are getting a lot of information, suppose you are collecting information about, say, a couple of criminals, right? So their whereabouts and what they do, etc., etc., right? Okay, and the more information you got about the same 2 criminals, the more you would know about them, right? More accurate would your information about those 2 criminals will be. But suppose with every bit of information there was an additional criminal being generated, right? Then your information would not for every criminal would not increase, right? Because the number of criminals to track also is increasing with the number of amount of information. Sure? So do you think? So in this case, suppose I have n observations. How many sigma squares you have to estimate? N. If I have n plus 50 observations, how many sigma squares you have to estimate? N plus 50. Right? The point is, each of the E hat I squares has only 1 degree of freedom. Each estimator that I am estimating will always have 1 degree of freedom. The degree of freedom will not increase with n. But the whole idea of estimating this properly is that the degrees of freedom will increase with the number of observations. But in this case, the number of parameters to be estimated will be the same, always the same as the number of observations. So degrees of freedom will always be 1. Right? And therefore, I cannot get consistent estimators using this type. So I will get unbiased estimators, but they will not be consistent. Right? If somebody asks you to show you estimators which are unbiased but not consistent, this is a nice example to do that. Right? Okay. So estimators will not be consistent. And therefore, we use an alternative strategy. We say that let sigma square I is some function of a set of variables called Zi. Yeah? So let sigma square I be some function of the set of variables called Zi. So sigma square I depends on some variable Zi. This Z could also be just contain just this X. So this Z could also be simply this X, or it could be some other external variable on which we have here. So we are saying that the variance of the error term depends on values of some variable Z. If you want, you can also make it X. So to keep things simple, we think of Z as X only. So we will say, so if I say that sigma square I is theta plus gamma xi, right? As x increases, as x changes, the variance of the error term also changes. Yeah.
So the variance of the error term is a function of xi, which is already there in the relation.
Yeah. So for example, let's take the classical case. Okay. So suppose you are trying to study the relationship between the amount of their income which people spend on food, okay, and their household incomes. So y-axis, you have the amount of the percentage of your household income which you spend on food is on the y-axis. On the x-axis, you have your household incomes. Right? What do you think the relationship would be? An upward sloping, downward sloping what? On the y-axis, you have the percentage of your income which you spend on food. On the x-axis, you just have your household income. Downward sloping, right? Why? Because if you are very poor, you will be spending most of your income on food. But as you keep on getting richer, the amount of income that you spend on food will keep on going down. Because there is a limit to how much you can eat. Right? Okay? Sure? Maybe it's also a curve relationship. But to keep things simple, let's keep it down. Right? So if I now have, so I have x and I have y, I take a downward sloping relationship. But the point is, if you are very poor, so what does this line tell you? This line tells you that for a poor household which have income equal, so if you take all poor households which have income equal to x1, what is their average expenditure, what is their average percentage of their income which is spent on food? That's what the conditional expectation gives you. Then we will use conditional expectation. Right? So it tells you, if you take all households which have income equal to x1, then on an average, what is their percentage that they spend on food? Now for poor households, not every household will spend that equal to what is given by the conditional mean, but the deviations around the conditional mean will be pretty small. All of you are poor, so on an average we spend 90% of our income on food, right? But the deviation, not each household spend 90%, but the deviation around that will be pretty small, right? So your error terms would probably be, say maybe something like this, yeah? You get some spread term, right? On the other hand, if it is a rich household, x2, then if you take all rich households which have income equal to x2, the percentage of their incomes which they spend on food can vary much more than in the poor case, right? So these households have spent only say 3% of their incomes on food, right? But one of the households had a wedding, so they spent a lot more on food, right? They were very rich household, they spent a lot, right? Some of them didn't spend much because they already they started doing some health things or whatever, right? Okay, so here you would expect the spread to be more, right? So you in general expect this spread to go up like this. Yeah? Right? So this is the classic case of the variance of the error term increasing with x. It could decrease with x, it could increase first and decrease later or do what you can. It could also depend upon some other third variable called z. Yeah? The point is, for simplicity, we'll assume that it depends upon theta plus gamma is. Now the next point that I'm going to ask you to tell me is that this is not a correct specification. This specification is a problematic specification. Sigma square I is equal to theta. So even when sigma square I depends upon xi in this model, it is not the right way to model sigma square I. Can you tell me why? Yeah, but that's what we are saying. That x goes up, sigma square I goes up. So this should not be a problem. The error term expectation x being equal to 0 is a different thing. What we here say is expectation EI square is correlated with x. So x and E are uncorrelated, but they are not independent. Yeah, because the variance of EI depends upon x. So x and E are uncorrelated. This is not the right way to model variances. Can you tell me why? See, variances have to always be positive. But suppose in this model, gamma is negative or theta is negative, then you can potentially have sigma square I also to be negative. So therefore this is not the right way to model the dependence of sigma square I on xi conceptually. Conceptually this is not the right way to do it. Sure? Everybody gets that? So what we will do is we'll have to figure out a way in which we can get the dependence of sigma square I in xi in such a way that you can never get negative sigma square. We need to find that dependence in a way in which we have to specify that function in a way so that sigma square I can never be negative. And a classical way of achieving that is to say yeah, sigma square I is equal to e raised to theta plus gamma xi, because e raised to anything can never be negative. Yeah, if what is e raised to, even if this whole thing tends to minus infinity, this will only tend to 0. So therefore you can never have this quantity negative by this specification. Right? So we say sigma square I is equal to e raised to theta plus gamma xi. We call this exponential heteroscedasticity. We call this exponential heteroscedasticity. Okay? Everybody gets this? Sure? So what we have from this is, take the natural log of both sides. Okay? Here is natural log of both sides. If it is natural log of e raised to gamma theta plus gamma xi, you will get theta plus gamma xi, right? Because all of you know log of e raised to alpha is equal to alpha. Sure? Okay. So log of sigma square theta plus gamma xi. Right. Now this we can use. So the point then is, we can then have a strategy. You have step 1. Right? So at the first step, what does this say? What does step 1 do? Do a normal regression of y of x, find alpha hat and beta hat, and find e hat I. Right? Sure? Then there's the first step. Yeah? Calculate e hat I square. Okay? And log of e hat I square is equal to so first we create e hat I square, then take the natural log of this and do a regression where log of E hat I square is the dependent variable and x is the independent variable. X is the independent variable. Sure? Right? So now, once you do this, you get the parameters theta plus gamma xi. Find the estimated value of this. Find the estimated value of this. Is theta hat plus gamma hat xi. Right? Sure? Right? Then calculate sigma I hat square is equal to yeah. Then calculate sigma hat I square is equal to e raised to theta hat plus gamma hat xi. You take exponential from both the sides, right? So calculate sigma hat square I is equal to e raised to theta hat plus gamma hat xi. E raised to theta hat plus gamma hat xi. And then use these sigma hat I squares, right? Then form your OMS, right? Then do one thing. Once you've got these, then do the transformation yi upon sigma hat I is equal to y star, right? Okay. Yeah, and do the regression, yeah, right? So beta hat FGLS will be obtained by